This is going to be the first video on contingent and reversionary benefits. This is covering contingent probabilities. The next video will cover contingent assurances, and then the following video, reversionary annuities. Okay, so this video, I'm expecting it to be a lot shorter than the next two, but it is foundational to the next two. So it's very important that you do understand it. And it's not just foundational. There are questions that can be asked specifically on contingent probability. So it's important that you understand what's going on here. Okay, now this is obviously from contingencies in actuarial mathematics. So if we're dealing with contingent probabilities here, then what we need to know first is what a contingent event is. So a contingent event is an event that depends on the order of death. So having two lives, now a contingent event could be the event that X dies before Y, or Y dies before X. And then we can also have some more specificity in there and say that X must die within a certain time frame, and then we don't care where Y dies, or both X and Y must die within a certain time frame, and there's an order to it. That's the type of thing that we're dealing with here. Okay, so these are statuses. So just as you had XY being the joint status, and this is just an annuity here, or you could have had the bar on top. This is a last survivor status from my previous two videos. Now we have XY and XY with these numbers on top of them. So these are also statuses that represent events, except they have a little bit more specificity to them. So this XY with the 1 on top of the X is the event that X is the first to die of X and Y. So XY, this status or this event, was the joint event, the event that either one of them dies first. Okay, but now I'm being more specific and I'm saying X must die first, and hence I put that line on top of the X. I could have also had the line on top of the Y, which would represent the different event, where the event that Y is the first to die of the lives X and Y. Okay, now this here represents a more specific case of the last survivor event. So the last survivor event does that. So this means that both lives must die. Okay, that's the event that both lives die. Now, both lives are going to die here in whatever time frame, but I'm saying that X must be the second of those two. Okay, so here, this event is the event that X is the second to die out of the lives X and Y. Okay, now, the two probabilities I want to define quickly is NQ XY with the line on top of the X, and this is the probability that X dies within N years, and Y can die any time after X. So note here, Y doesn't have to die within N years as well. Y just has to die after X, and X has to die within N years. Okay, then this probability is the probability that both X and Y die within the next N years, and X is the second to die. Or you can write it like this: the probability that X dies within N years and Y dies before X, which implies that Y will also die within N years. Okay, cool. So an important thing to note is that NQ XY with the 2 on top of the X there is different. It's not the same as NQ XY with the 1 on top. Now, this is misleading. You might think that these two are the same because in both instances, Y is the life that dies first. But the difference is that this probability refers to when Y dies within N years, and we don't care when X dies, as long as it is after Y. Okay, so X can die after N years. But here we're saying that X must also die within N years. So X must die between Y's death and time N. Okay, and then similarly, NQ XY with the 1 on top of the X does not equal to NQ XY with the 2 on top of the Y, for the exact same reasons as this. Okay, so if we have probabilities from the life table, probabilities of survival or death for lives X and Y, and we have their forces of mortality. Now we want to go ahead and calculate these two probabilities. How do we go about doing that? Okay, so NQXY here is equal to, now I'm going to start with the final answer because it's a lot more intuitive, and then I will go back and show you the route that we take to get there and why it actually is true. Okay, so NQXY equals the integral from 0 to n TPXY mu x plus t dt. So what I'm saying here is that any time between time 0 and time n, at each of those time points, x and y must be alive, and then at that specific time point, x must die. Okay, and I don't care about y dying, which is why I'm only including a force of mortality or rate of transition here from alive to dead for x only. Okay, so I'm saying that between time 0 and time n here, they must both be alive at this particular point in time t, and then x must die at that exact point in time. And then I'll weight that probability there. And then at this exact next point in time, they must both be alive, and then what happens if x dies there? Okay, so that's me calculating this probability here, taking into account all the possible places where x can die. But we're saying that when x dies, y should have been alive at that point. And obviously x should have been alive at that point as well, because he's only dying at that point. Okay, so x and y both survive to this particular point in time, and then x dies. Okay, and that can happen at any point in time between time 0 and n. Okay, so that's the final answer, and that's very intuitive to us. But how do we get here? Okay, so NQXY equals to, now I'm going to write out a double integral, and then I'm going to explain exactly how it works and why it's true. So the integral from 0 to n, and the integral from t to infinity, tpx mu x plus t spy mu y plus s ds dt. Okay, so why is this double integral true? Okay, well, let's think about it. Okay, so what does this probability represent? It represents x dying within n years and x dying before y. Okay, those are two simple things that I said there. And writing that in terms of things that we know, that is essentially x dying before y and x dying before n years is up. Okay, that's it. We're calculating the probability of that event. Okay, so how do I write this event out? Well, if this axis is my tx axis and this axis is my ty axis, now I ask you, how do ty and tx relate? Well, both of them are non-negative because it's complete future lifetime, so they can't have a future lifetime of a negative number. Okay, so both of them are going to be positive, which means in this first quadrant. Now I'm also saying that how do x and y relate? Well, as tx grows in time, so as this lifetime for a life now aged x grows, what happens to y? Well, it should also grow at the exact same rate because it's dealing with time here. So tx and ty are linearly related. Okay, and hence I write that line there, the ty equal to tx line. So after 10 years, if they're both still alive, let's say, or let's say they both die. Okay, let me not say it like that. Let's just say that as a year passes, tx goes up by 1 and ty also goes up by 1. Okay, so as time progresses, they progress linearly in the exact same way. Okay, I'm not going to overcomplicate it. So that's their relationship between the two. Now, what I want is, on this graph, I want this event, tx being less than or equal to ty. So what does that mean? That means that tx should be a shorter distance from this axis than ty is from this axis. So what does that mean? If this is where tx and ty are equal, then it means that we must sit somewhere up here above this line, okay? Now, how do I know that's true? Because any point above this line will have a y-coordinate greater than the x-coordinate, okay? So we know then that that event gives rise to that. But simultaneously, I must have tx being less than or equal to n. So if here is time point n, then that goes all the way up here. I need tx to be on that side, and so I only then deal with that area. Okay, simple enough. Now, this defines my bounds for this double integral. Okay, so I'm going to use the placeholder variable for tx. I'm going to use t, and then for ty, I'm going to use s. So this here is the s equals to t line. Okay, so how do I integrate this area? Okay, let me remove this shadowing so I can explain it to you. So in order to cover this area, I first am going to integrate in terms of t. Sorry, in terms of s. Okay, so as I integrate in terms of s, it means I'm covering distance in that direction there. So when I integrate in terms of s, what I'm essentially doing is I'm integrating from this particular point upwards. And then as I integrate in terms of s, I must also integrate in terms of t. So I integrate like this. From this line, s equals to t, to infinity. And then next to that, I integrate up from that point to infinity. Then from that point to infinity. And the next point to infinity. So the direction in which these arrows are pointed is the direction in which I'm integrating for s. And the order in which I'm drawing the arrows is the integration in terms of t, okay? And integration in terms of t stops at n because I stop drawing arrows at n, okay? So I hope that makes sense. A lot of this should just come from your understanding of double integrals, and that's not really the point of this video. So if you don't understand double integrals, try and find a different YouTube video to understand that. But this should give you basic enough understanding. Okay, so here my inner integral is the direction of these arrows, and all these arrows start on this line, s equals to t. So I'm integrating in terms of s from t, and they finish, when do they finish? Well, they don't finish anywhere, they go all the way to infinity. So integrate until infinity, and then I draw these arrows all the way from 0 to n, so in that direction there. Okay, now why do I have this in here? Well, because I'm dealing with tx and ty, okay, and the PDF of tx is tpx mu x plus t, and the PDF of ty is spy mu y plus s. Simple as that, okay? They both have their own probability density functions, and so I'm integrating over their probability density functions. Okay, perfect. So now this is where we can eventually get from this line to this line. So I'm going to integrate now. So this first integral is in terms of s. So basically, all that I'm doing is this here. So these, I'm evaluating this integral. So what is this integral? Let's understand it. Well, y must be alive up until time point s, and then y must die at time point s. Okay? That's what it's saying. And then this s can slide from t to infinity. So that means y must be alive all the way up until time t. And then at any point from t to infinity, y must die. So this is the probability that y is still alive at time t. Okay, that's what it evaluates to. So this equals to 0 to n t p x mu x plus t times by t p y dt, and then this equals to that line there. Okay, so that's how we prove this one. Okay, now let's deal with NQXY, where X here is the second to die and X dies within N years. Okay, so similar logic here. I'm going to write out the double integral and I'll explain how it works. So it's from 0 to n, and then from 0 to t, tpx mu x plus t, spy mu y plus s ds dt. Okay, so once again we start with the events. What events am I dealing with here? Well, I know x must die within n years, and I know y must die before x. So what I'm essentially saying then is tx must be less than or equal to n, and then I'm also saying that ty is less than or equal to tx. So y dies before tx and tx dies before n years. So the complete future lifetime of x is smaller than n years time. Okay, cool. Now we must draw this graph out again in order to understand how we're going to integrate this. So let's draw this graph here. Here's my tx and here is my ty, and that is how they relate. And then here is my time point n. So I need tx to be less than or equal to n, which once again is all of that. But now ty must be less than or equal to tx. So in other words, everything under this line. So the intersection of those two areas is just that area there. Okay, so here now, when I'm integrating, I integrate the constants on the outside again and my variables on the inside so I can actually evaluate this thing. Okay, so the variables on the inside, what is the variables? Well, this is the variable bound, okay, because it changes as tx changes and as ty changes, okay. This is a constant bound and this is a constant bound of this area, but this here is the variable bound. So this variable bound that defines this region should be in my inner integral. So this is s equals to t again, where I'm going to find the ty, the placeholder variable for that will be s, and for tx, the variable will be t. Okay, so in order to cover that area, I must integrate from 0 up until t, from 0 up until t, 0 up until t, so the direction of my arrows is the integration in terms of s, and the order in which I draw them is the integration in terms of t. So I integrate in terms of s, and I continue to integrate until I cover this entire area, and that means I'm integrating from 0 up until t, because all the arrows, the base of them start at 0 and end at t, and my first arrow begins at time 0, and my last arrow ends at time n. Okay, so that's how I get my two bounds, and then once again, these are just my PDFs inside here of tx and ty. Okay, so this equals to the integral from 0 to n tpx mu x plus t, now tqy instead. So in the previous one, this was tpy, but now it's tqy. So the difference is that y must be dead by the time that x dies. But here, y should be alive at the time that x dies. Okay, so intuitively, we can understand this as at any time point between time 0 and n, x must die. And hence, I've got this force of mortality here for x. At any time point, I'm going to slide this force of mortality all the way from 0 to n. And at this time point that x dies, x should survive up until that point in time, but y should already be dead, so that I can fulfill this where x is the second to die. Okay, but then x must also die before n is up, which is why I'm integrating by multiplying this force of mortality as well between 0 and n. Okay, fine, that makes sense. Now we can actually take this further. Again, by the way, how did we arrive from this line to this line? So we integrate everything here that is s. So basically what we're doing is this here, and we evaluate this integral, and this integral is the probability that y dies between time 0 and time t. So the probability that y is dead within the next t years. Okay, cool. Now, how can we simplify this? Well, if I change tqy to be one minus tpy, okay, then I can multiply that into the brackets, okay, and I'm left with this. And this doesn't really look like a 0. Okay, 0 there. Okay, now just integrating this term here from 0 to n is the probability that x dies within n years. Okay, and then integrating this from 0 to n is the probability, take this negative out the integral, that x dies within the next n years, and x dies first. How do I know that's true? Well, look here. It's the exact same as that. Okay, fine. That makes a lot of sense. Now, what this actually gives us is another result. So nq x2y is equal to this, which means that nq x2y plus nqx1y equals nqx. And this should make intuitive sense to us as well. So why does it make intuitive sense? Well, here I just want the probability that x dies within n years. And when I introduce the life y to this equation, all that can happen is x either dies before y or x dies after y. And if x dies before y, then here's the probability. If x dies after y, here's the probability. And I sum those two up. But in both cases, x is dying before time n. Okay, so this intuitively makes sense to us. Okay, now another thing, another formula that we should know is nq x squared y equals to nq xy with the 1 on the y minus npx n qy. Okay, so in this form here, it's not so intuitive. So what I recommend doing is trying to have, if you have to try and make sense of equations, is to try and have them such that you're only adding probabilities, because it doesn't really make sense to us intuitively to subtract probabilities. So think about it like this. If you have the probability of 3 events occurring, okay, and 2 of these events make up this larger event, it's very difficult for us to conceptualize what subtracting probabilities is, okay, where this event happens but this part of it doesn't happen. That's the type of thing that it is. But it's much more difficult to conceptualize than to just remanipulate the equation and then to think of it as these 2 events occurring together just represents this other event. Okay, so I'm gonna change the order of this to be nq x2y plus npx nqy is equal to nq xy1. Okay, now here is the simplest to interpret. So just because it's one side of the equation. So what is this? This is x and y. So out of x and y must die first and y must die within n years. We don't care whether x dies within n years or not, but x must die after y. Okay, and then how do we represent this in terms of other probabilities? Well, let's think about it. When I introduce now this other side of the equation, what I'm essentially saying is here X and Y both die within n years, which is part of this, okay? Because this here is Y dying first within n years. And here I'm saying X and Y both die within n years, but Y is still dying first, okay? Now, the rest of the answer is where still Y dies first, that's the important part, but now X must survive the n years, okay? So Y dies within the n years, but X survives the n years. Y dies within n years, X also dies within n years, and X dies second. And that equals to the event where Y dies first within the next n years. Okay. So the thing that's important is both of these represent Y dying first, but the only difference between them is here X dies within n years, here X doesn't. Okay. And that makes up together, whether X dies within n years or X doesn't, that makes up this probability. Okay. But so long as Y dies first. Okay, now, another thing that's important is NQXX. So, because I have two X's here, I'm not saying that they are the same life. I'm just saying that we're modeling their mortality with the exact same mortality, and I'm saying that they are now aged X. So they're both aged X now. So NQXX will be equal to 1 over 2 NQXX. Okay, so let's understand this. Why is this intuitive? Why does this make sense? Okay, well, here I need one of these, the certain, let's say I'm going to call them two lives, XA and XB. So I want XA to die first, okay? And XA must die within n years. But now, since they both have the same mortality, it's no different. NQX1 X there is equal to NQXX with the 1 on the other X here. They're no different because they have the same mortalities. The probability that this X dies first within n years should be the same as the other X dying within n years and dying first, because they have the exact same mortality. Okay, so if those two then have the exact same mortality, then what I'm saying is that here it's the joint probability that one of them must die within n years, but I'm not specifying which one. And if one of them must die within n years, it can be either of them. So I must divide that by 2 to get that a specific one of them must die first, because the other case is where the other one dies first. Okay, now the next thing is, so let's get rid of that. Next thing that we need to know is QX here, infinity QXX is equal to infinity QX x squared is equal to 1 over 2, since okay, so what am I saying here? Well, infinity QXX equals 1 makes sense because both of them will die before the end of eternity. Okay, that happens with certainty. Now, which one dies first? They both have equal chances of dying first. So whether X dies first, this XA here dies first, or whether XA dies second, it's equally likely to happen because we're modeling them with the same mortality. Okay, now the next thing that we must note is NQXX2 should be equal to 1 over 2 NQXX with the last survivor, which should equal to 1 over 2 NQX squared. Okay, now quickly, this should make sense to you from the previous video because generally it holds that NQXY last survivor probability there equals to nqx times by nqy, okay? But now both of them are x, so that just becomes squared. Okay, so this line should make sense. And this line follows similar, this equality follows similar logic to what we did here. So what this probability represents, nqxx, the last survivor, is that the last one to die must die within n years. Okay, the last one to die must die within n years. But this can happen whether each of them could die second. Okay, so this one doesn't care which one dies second. I must just say that one of them will die second, but as long as both of them die within the next n years. Okay, so this probability is twice as big as the probability when I specify the person that must die second. Okay, in other words, nqxx to there plus nqxx to there should equal to nqxx bar. Okay, that's everything I wanted to cover in this video. If anything is unclear, please leave a comment down below. I'll try my best to tend to it and clarify what I was saying. Thanks for watching.